So let us now discuss certain properties of Zn star. Zn star is the set of all integers modulo n which are co-prime to n. So alpha belongs to Zn star means alpha is co-prime to n. That means GCD of alpha and n is 1. Now order of alpha, already we define order of alpha to be the least positive integer t. Suppose order of alpha is t. What we mean by that? That means t is the least positive integer such that alpha to the power t gives you 1 modulo n. So alpha to the power t means if you raise it to the power alpha square alpha cube, and t is the least positive integer such that alpha to the power t equal to 1 modulo n. In that case, t is the order of alpha. Now, if the order of alpha is phi n, means if alpha belongs to Zn star, alpha to the power phi n is always 1 congruent to 1 modulo n. That is Euler's theorem. That is Euler's theorem. Now, if the order of alpha is phi n, then alpha is said to be a generator or primitive element of Zn star. In earlier class, we have seen that this result is order we define in this way: t is the least positive integer such that a to the power t is congruent to 1 modulo n. But by Euler's theorem, we already know that a to the power phi n is congruent to 1 modulo n. So it can be shown that this order t is a divisor of phi n. So in a next fact, it is means not only that, means if t is the order, and for any s we have this congruence equation: a to the power s is congruent to 1 modulo n. Then this s has t as a factor. T divides s. Okay, so if order of alpha is this phi n, that means no other positive integer, no other positive integer which is less than phi n, and that actually is a divisor of phi n, is order of alpha. In that case, alpha is said to be generator or primitive element. Okay, so in that case, this is the cyclic group. This Zn star, it constructs a cyclic group under the multiplication operation. We say alpha is a primitive root modulo n. This alpha, which is a generator or primitive element of Zn star, it is also sometimes called, we call it alpha is primitive root modulo n. Primitive root modulo n. Now, so this Zn star, whenever we get a generator, it is a cyclic group, and the properties of this generators of Zn star, these are there are a few properties, 4 properties we are going to discuss. So, under which condition under which restriction on n, this Zn star forms a cyclic group? That means it has a generator. It has a generator if and only if the value of n is either 2 or 4 or some prime, odd prime to the power k, or 2 times this prime to the power k. P is prime, odd prime, and k is greater or equal to 1, some positive integer. In particular, if p is a prime, that means you are considering Zp star p prime. It always has a generator. Now, if alpha is a generator of Zn star, then alpha is a generator of Zn star. Then Zn star is essentially consisting of all the elements, all the powers of alpha. Is alpha to the power I modulo n, such that where this I lies between 0 to phi n minus 1. Zn star can be written as alpha to the power I modulo n, such that this I varies from 0 to phi n minus 1. So how many i's we are allowing? There phi n many i's. So alpha to the power those values modulo n gives you the whole Zn star. Okay, so Zn star we already have observed that this is the number of elements less than n and co-prime to n. Phi n many elements, and all those elements can be written as powers of alpha. Alpha to the power I lies between this and this, 0 to phi n minus 1, including 0 and phi n minus 1. Now, if you know one generator, okay, if you know alpha is a generator of Zn star, or this is primitive root modulo n, alpha is a primitive root modulo n. Okay, so what are the other generators? By this formula you can determine. Okay, so if alpha is a generator of Zn star, then alpha to the power I modulo n is also a generator, provided I and phi n are co-prime. Okay, so how many generators Zn star can have? Phi of phi n. Why? So if you consider this condition, this is essentially the B equal to alpha to the power I modulo n is also a generator of Zn star if and only GCD of I phi n equal to 1. So how many these i's are there that are co-prime to phi n? How many i's are how many integers modulo n are there which are co-prime less than n and co-prime to n? That is phi n. So how many integers are there which are less than phi n and co-prime to phi n? That is Z phi n star. So this is essentially this set. If you consider, instead of Zn star, if you consider Z phi n star, it is set of all integers I belongs to Z phi n. Belongs to Z phi n. That means integers less than n and co-prime to phi n. Less than n, this I, alpha to the power I, these are the elements of Zn star. So Zn star elements can be written as powers of alpha. And this I varies from 0 to phi n minus 1. So these i's are less than phi n. So how many integers are there? How many i's, these powers you can find, so that which are co-prime to phi n. That is essentially phi of phi n. That is the cardinality of this set. Z phi n star equal to set of integers I belongs to Z phi n. That means I is ranging here 0 to phi n minus 1. Z is less than n and co-prime less than n, less than phi n. I belongs to Z phi n means I is less than positive integer less than phi n. So that I and phi n, this I and phi n are co-prime. This set, explicitly we denote this set by essentially Z phi n star. So cardinality of this set is phi, cardinality of this set is phi of phi. Okay. So how many generators Zn star has? Phi of phi. And another thing is alpha belongs to Zn star is a generator of Zn star if and only if alpha to the power phi n divided by p is not congruent to 1 modulo n. For each prime divisor, for each prime divisor p of phi n. Okay, you can prove all these things. Means proof of this first one, it is not that straightforward. In number theory, we covered this proof. Okay, so this is not just I cannot cover this proof in one class, and we are not going to discuss the proof here. Only to find the generators, or means in problem finding some solving some problems, we are going to utilize these properties. Okay, so we will design certain algorithms that will help us to find the generators, their order. All for those we are going to utilize these facts. Okay, so what we have learned, Zn star, this is cyclic, multiplicatively cyclic group. That means it has a generator. Generator is called primitive root modulo n, or primitive element. So it has a generator if n is either 2, 4, p to the power k, or 2 times p to the power k, where k is a positive integer and this p is a odd prime. P is an odd prime. Okay. And second property means alpha is a generator, means generator of this means every element of these can be written as powers of alpha to the power I modulo n. Every element here can be written as generator, means it can be written as every element here is a power of alpha. So alpha to the power I, how many elements it has? It has 0 to phi n minus 1 elements, means total phi n elements. It has phi n elements. So this I ranges from 0 to phi n minus 1. Okay. So this one is straightforward. This you can prove in algebra, in abstract algebra. Using abstract algebra, you can prove this thing. First one is not that straightforward, and this one is also you can prove this. The number of how many generators you will have? Phi of phi n. This Zn star will have phi of phi n many generators. And this one also it can be proved. It says that if alpha is a generator of Zn star, then alpha to the power phi n divided by p not congruent to 1 modulo n, where p is a prime divisor of phi n. Yes, it comes from the definition. Alpha is a generator means its order is phi n. So if you take if you take other divisors of phi n, which is less than phi n, means this is 1 factor of phi n. So all those values will not alpha x to the power, those values will not give you 1 modulo n. And it can be proved that only checking these for prime factors of phi n is sufficient. Okay, to check, and this is if and only condition. If alpha is a generator, then for every prime divisor of phi n, it should not be 1 modulo n. And if for every prime divisor of phi n you can show it is not congruent to 1 modulo n, then alpha is a generator. Okay. Okay. Okay, now some simple exercises, examples. J21 star, this is not cyclic. Why? Because 21 means it cannot find a primitive root modulo 21. Why? 21 is not of this form. It is product of 2 primes. It is product of 3 and 2. It is product of 2 primes. So J21 has no primitive element or generator. And because it means it does not contain any element of order 521. 521, if you find 521, it is 12. Okay. And 21 is not of this form, so that's why it is not this group is not cyclic. J25 star, it is 5 square. Okay, p square 5 square, so it is cyclic. From this theorem only you can argue this is a cyclic group. So if alpha is a generator of this, you can show that alpha is a generator. I'm not asking you to show that. I'm just saying this is cyclic. You can easily verify because it is having this form. And suppose alpha equal to 2 is a primitive element. Now, can you find other primitive element? Utilizing this formula, you can find other primitive elements. So other primitive element will be, this is 1 generator. So if you know 1 generator, you can find other generators by taking the powers of alpha and reducing modulo n. Provided this I, this power, it should be co-prime to phi n. You have to choose this power co-prime to phi n. So you calculate phi n, 525 you calculate, 525 it is 16. 525, no, its calculation is 25 into 1 minus 1 by 5. 525 star, this is 20. So this calculation is wrong. You just check it, okay? You utilize the formula. 525 square means phi of 5 square. That is 25, 1 minus 1 by 5. This formula you have to. This is not phi is multiplicative, but you can write phi mn to be phi m into phi n provided m and n are co-prime. So this is not valid thing, okay? So this is the formula. 525 is 20. So 20 elements, you can just list down 20 elements, and you can find the order also. And how many generators Z25 star will have? Phi of phi n, phi 25. That means phi 25 is 20, you take phi of this 20. That many generators it will have. I have calculated this. Alpha equal to 2 is a generator. Phi 25 is 20. So order of alpha should be 20. So order of this is a generator of Z25 star. Its order is phi 25. And order means how many elements are there? And primitive element phi. This is having phi n elements, and this generator means the order of alpha should be phi 25 20. So phi of phi 25 means 8. It means 8. So it how many generators it will have? 8 generators. So one generator is given. If one generator is given, then you can find all the other generators by simply raising this alpha, this 2, this 2 alpha to the power I, where I is co-prime to phi 25. I is co-prime to phi 25. So you list all the elements which are co-prime to 20, all the integers less than 20 which are co-prime to 20. So this list is essentially 1, 3, 7. So this list you can just set of integers in Z20 which are co-prime to 20. So these are the list. There are 8 elements here. 8 elements I list down, and therefore the other generators are given by alpha to the power I is I from this set modulo 25. So answer, you have to, if you are asked to find all the generators given one generator alpha equal to 2 alpha, you have to find all the other generators. So you have to take you have to give the solution after reducing modulo 25. So you can just list down all the generators are 2 cube, 2 to the power 7, 2 to the power 9, 2 to the power 19 modulo 25. You have to reduce them. Okay, you have to reduce them. So this way you can reduce. So this is essentially should be your answer. This one will be answer. So you have to reduce modulo 25. Okay. So there are certain calculations. So the problem is here, if you are given one generator, you can find other generators. Also, you can check whether this Zn star is cyclic or not. It has a primitive element of generator or not. Given one generator, you can find other generators. The problem is how to find one generator. That is not that trivial problem. Means we don't have any efficient algorithm to find the generator except brute force. We generally what we do, we start from a very the smallest prime and check whether it is a generator. And to check whether it is a generator or not, the condition we use this one. Condition we use this one. We have to check. We have to find all the prime factors, all the divisors of phi n, and check whether this condition holds or not. Okay, this condition, this number 4 condition. Okay, so I have done the same exercise with Z13 star. Okay, find all the generators. So here the first generator was not given. So I have find out one generator alpha equal to 6. How to find the generators of Z13 star? So that is means if it is very small modulus, then by exhaustive search you can do. But if it is very large, then essentially we don't have any efficient algorithm for that. Okay, I will discuss. I will discuss this problem. So generator, if you are given one generator, you can find other generators. But finding one generator, we have one problem here, one fact here. So this problem, it says, For which of the following moduli n do primitive roots exist? So immediately you can find. So just check whether it is of the required form. So 20 is 2 square into 5. Okay, so it is not 2 times prime power to prime power. So it is not, so for this, so we don't have primitive element. So you can identify this is a prime, it has primitive root exists. For this one also primitive root exists. So this is 2 times a prime power. Yeah. So this has primitive root, this has also primitive root. Modulo this has primitive root. Now how many primitive roots? So the next question was, in case primitive root exists, how many? So this is phi of phi n. So if n is this, you can easily calculate these values. You know, you can apply that. Now the some natural questions. First question is existence of primitive roots for which moduli n primitive root exists. You can answer this. Second question is finding the primitive root. So determining a primitive root. This problem we are going to discuss now. And computing orders. So you have to find the order of A modulo. In this notation, essentially we are going to use. So order of A modulo n exists provided n and A are co-prime. Okay, this order defined provided A and n are co-prime. And another problem we are going to discuss, this is discrete logarithm problem. It says that if G is a primitive root modulo n and A is some integer such that GCD of A n equal to 1. So G is a generator of Zn star, A is any integer and A is any integer and you have to find this J. You have to find this J such that G to the power J is congruent to A modulo n. So G is given, A is given, n is given. So you have to determine this power J for which this essentially G to the power J equal to A. So J is the discrete log. This is the discrete log of A modulo A to the base G. Okay, so how to find the discrete log? This is called discrete log problem. This is called discrete log problem. Given G, so you have to essentially find the value of G for which G to the power J is congruent to A modulo n, where G, A, n all are given. Only unknown is J. So you are working modulo n in the power, you have to work modulo phi n. Okay, so you have to find this J modulo phi n. Such that this condition. Now, this is called discrete log problem, and we will discuss that this problem is not very easy. Okay, if n is very large, so finding this discrete log of A is not that easy. So all that we are discussing so far is it is essentially modular arithmetic. Okay, we are discussing modular arithmetic. So the question we didn't answer is finding the primitive root, determining the primitive root. How to determine that? So for that we have this result. Okay, determination of primitive roots, finding primitive root when they exist. We can convert this problem with finding primitive root when they exist. That means finding primitive roots of n, where n is having the desired forms. We know that for what forms of n it will have primitive roots. So finding primitive roots when they exist, we can convert this problem into determination of primitive roots modulo A prime. Okay, so we know primitive roots exist for n when n is either 2 or 4 or some prime to the power k, p to the power k, or 2 times p to the power k. K is integer, positive integer, and p is some prime. So if you are finding primitive root modulo A prime power or 2 times prime power, you can convert this problem into determining the primitive root modulo A prime, p. Okay, so primitive element modulo p to the power k, you can convert it into the problem. This actually boils down to the problem of finding the primitive root modulo p. So it actually comes from this result. This result also, it is, the proof is not trivial, and we are going to state the theorem only, and we are going to utilize this theorem to solve certain problems, the generators, to find the primitive roots. So in each of the following cases for a modulus n in which primitive root exists, the following rules show how primitive roots can be found. Okay, so the thing is, if you know that G is a primitive root modulo an odd prime power p to the power k. So if you have a primitive root modulo p to the power k, then this G or G plus p to the power k, whichever is odd, will give you the primitive root modulo 2 times p to the power k. So if you know the primitive root modulo p to the power k, primitive root of p to the power k, then you can find the primitive root of 2 into p to the power k. Okay, so for 2 into p to the power k, the primitive root will be either this G, which was the primitive root modulo p to the power k, or G plus p to the power k. Okay, and the next one states, if G is a primitive root modulo an odd prime, so if you know a primitive root modulo an odd prime, then for modulo p square, you can find the primitive root. So if G is a primitive root modulo odd prime p, then G or G plus p, whichever is odd, will be the primitive root modulo p square. Okay, so knowing the primitive root modulo p, you can find the primitive root modulo p square. Knowing the primitive root modulo p square, you can find the primitive root modulo 2 into p square, like that. And here the last one is, if p is odd prime and G is a primitive root modulo p square, then G is also a primitive root modulo any higher prime power. If p is a primitive root modulo G, if G is primitive root modulo p, then G is also a primitive, sorry, p is a prime and G is a primitive root modulo p square, then G is also a primitive root modulo any higher power. Okay, so how can I convert this problem finding primitive root when they exist to this problem finding primitive root modulo a prime? Okay, so I will first find a primitive root modulo. Suppose I have somehow I found G is a primitive root modulo p. Then I can utilizing this fact, I can get the primitive root either G or G plus p, whichever is odd, is a primitive root modulo p square. Now I know a primitive root. From knowing primitive root modulo p, I know primitive root modulo p square. Now apply this one. If G is a primitive root modulo p square, then G is also a primitive root modulo any prime power. Now apply this one. If I know G is a primitive root modulo any prime power, then either G or G plus p to the power k, whichever is odd, will be primitive root modulo 2 times p to the power k. So if you know the primitive root modulo a prime, then you can find primitive modulo prime square. You can find from there primitive root modulo p to the power k, and you can find the primitive root modulo 2 times p to the power k. So all the primitive roots for all the integers for which it exists, you can always determine utilizing these 3 facts. So this is essentially giving you an algorithm. The problem is how to find, at the first place, how to find the primitive root modulo a prime. For this, we don't have any efficient algorithm. Okay, we start from the smallest possible primitive root and check its primitive, whether it is primitive element or not. Then we keep on increasing it. Next possible primitive root. That means next relatively co-prime integer with n. Next integer which is co-prime to the given modulus. Okay, that way subsequently we try to check whether it is primitive element or not. So finding the primitive element, we have to keep on powering. One element is primitive or not, we have to keep on powering. Means alpha is primitive element, primitive root modulo phi n means primitive root modulo n means its order must be phi n. And if you take other factors of phi n, that is essentially less than phi n, other prime factors of phi n, and you have to check that alpha to the power phi n divided by that prime is not 1 modulo n. Okay, so here one example is given here. So if you consider your modulus to be n is not in the required form, so it does not have any primitive root modulo. There does not exist any primitive root modulo 8. What about 7? Primitive root modulo 7, you can check 3 and 5 are the primitive root modulo 7. So 3 is the primitive root modulo. So primitive root modulo 7 are 3 and 5. So primitive root 3 is also a primitive root modulo 7 square. 5 is also a primitive root modulo 7 square. We have seen that if P is a primitive root, if G is a primitive root modulo a prime or prime, then either G or G plus P will be primitive root modulo P square. So 7 square modulo 7, we know 3 and 5 are primitive roots. So modulo 7 square, you can this 3 is a primitive root modulo 7 square. Either 3 or is 3, this is 3 or 3 plus p, whichever is odd. Okay, 3 is a primitive root modulo 7 square. Also 5 is also a primitive root modulo 7 square. So in this case, both are primitive root. Means G and G plus P both are primitive root. You can see if you consider 3 is a primitive root, and 3 plus P means 3 plus 7, 10 modulo 7 you have to take. So 3. So it is giving you 3. If you take it is 3 and G plus P is 3 plus 7. So it is also giving you 3. Modulo 7 you have to take. Okay. So 3 is a primitive root modulo 7 square. You can check also. You have to check that. These are the possible things. You have to check that. 5 is also a primitive root modulo 7 square. So 3 is a primitive root modulo 7 to the power k also for any integer k greater than 2, positive integer. Also 5 is a primitive root modulo 7 to the power k. And 3 is a primitive root modulo 2 times 7 to the power k. 5 is also 7. And how many primitive root 7 will have? Phi of phi 7. If you calculate this value, this phi 7 is essentially 6. 7 is prime, so phi 6. Phi 6 is 2. So 2 primitive element, you can check this. Okay. So I can ask you find the primitive roots modulo means whether primitive root modulo 98 exists or not. If it exists, find. Okay, this type of questions, simple questions I may ask. Okay. Okay. Now this is another thing that we have to learn. This is called Zn star. All the elements in Zn star can be divided. N is any integer, and A belongs to Zn star. We say that A is quadratic residue or square. Quadratic residue modulo n or square modulo n. What does this mean? That means A can be written as square of some integer from here. So you can find A is quadratic residue modulo n or square modulo n. Means there exists some integer here, some x belongs to Zn star, such that A can be written as square of x. So A is a square modulo n. That means A is some x square, x is in Zn star modulo n. So square modulo n same as quadratic residue modulo n. Okay, this concept we need while we will design Revit crypto system. We are going to utilize this. Essentially, this quadratic residues plays an important role in designing this Revit crypto system. We will see that. And if no such exists for A, for which A can be written as square like that, then it is called quadratic non-residue. Okay, so when we consider Zn star, 0 is excluded. 0 is excluded, and all the elements which are quadratic residues, we denote them by this set. Set of all quadratic residues modulo n is denoted by Qn, and the set of all quadratic non-residues are denoted by Qn bar. This is Qn, this is Qn bar, and this we define for any integer n, for which means for any integer, not necessarily prime. Okay, n can be composite also, but if it is prime, then we are having some interesting properties. So here, before that, we just mentioned here, Zn star does not belongs to 0 does not belongs to Zn star. So 0 is neither a quadratic residue modulo n nor a quadratic non-residue modulo n. It should be not equal to, okay, not equal to. It does not belong to Zn star means it is not a quadratic residue, it is not a quadratic non-residue. It should be not equal, okay. Now, as I said, if you consider Zp star instead of this n, I am taking this n to be an odd prime. So P is an odd prime and alpha is a generator of Zp star. Then A belongs to Zp star is quadratic residue modulo P if and only if A is alpha to the power I modulo P, where I must be even integer. Even quadratic residue means A is quadratic residue. This means A should be written as powers of, A should be written as square of some integer. So this will be square of some integer means I must be even integer. It is even only condition. You can take this as a small exercise. A proof of this as a small exercise. Okay, so in case P is prime, Zp star, all the elements in Zp star, how many elements are there in Zp star? Pi P, that means P minus 1 elements. So half of them are quadratic residues and half of them are quadratic non-residues. These proofs, we will discuss these proofs, okay? A few proofs we will go through. So half of the elements in Zp star are quadratic residues and half of them are quadratic non-residues. Okay, actually it follows from this fact. If you can prove this thing, from there you can argue this one. Okay. Suppose for Z13 star alpha equal to 6 is a generator, you can check that. Okay, alpha equal to 6 is a generator of Z13 star. If you list the powers of alpha, this powers of alpha, okay, powers of alpha. List the powers of alpha. So alpha to the power I is 0, 1, 2 up to Z13, right? Phi n minus 1. Phi n is, this is actually phi n. Phi n in 13, phi 13 is 12. So you have to take the powers up to 0 to, means from 0 to phi n minus 1. Phi n minus 1 means 11. So 0 to 11, take all the powers and raise 6 to the power those powers. 6 to the power 0 is 1, 6 to the power 1 is 6 to the power 2 is 10, 6 to the power 4. You can find the quadratic residues in this way. So all the even power, 0 is also considered as even. Okay, even power. So this is even power, this is even power, this is even power, even power, even power. So all the quadratic residues are this 1, 10, 9, 12, 3 and 4, and quadratic non-residues are remaining. So Zn star, Zp star, half of them are quadratic residues, half of them are quadratic non-residues. So all the elements, all the powers of alpha to the power I, for which I is even, those elements are quadratic residues, and other elements are quadratic non-residues. Okay. So in particular, if you have if your n modulus n is a product of two prime numbers, n be product of two distinct odd primes p and q, n equal to pq, p and q they are co-prime. Okay, GCD odd primes, they are odd primes, p and q both are odd primes. Then a belongs to Zn star is a quadratic residue modulo n if and only a is a quadratic residue. So A is quadratic residue modulo n if and only A is quadratic residue modulo p and A is quadratic residue modulo q. So A is quadratic residue modulo n, where n is product of two primes, distinct odd primes, if and only A is quadratic residue modulo p and A is also quadratic residue modulo q. Individually, A has to be quadratic residue modulo p and quadratic residue modulo q. So from here, it follows that how many quadratic residues modulo n exist? N is composite, particular this form. Okay. So number of quadratic residues modulo n is equal to number of quadratic residues modulo p into number of quadratic residue modulo q. Now when p is prime, the value I know this is p minus 1 by 2. How p minus 1 by 2 quadratic residues modulo p, and q minus 1 by 2 quadratic residues modulo q. So how many quadratic residues modulo n we have? This is p minus 1 into q minus 1 by 4. That means this is essentially the value is phi n. This value is p minus 1 into q minus 1 is phi pq, right? Phi pq. Phi pq is phi p into phi q. That means p minus 1 q minus 1. This is phi n. This value is phi n. And therefore, so in this out of these elements in Zn star, this phi n by 4 many elements. So how many elements we have here? I have total phi n many elements in this set. Out of them, phi n by 4 many elements are quadratic residues. So remaining 3 into phi n by 4 many elements should be quadratic non-residues. Okay, so we have observed that if p is prime, half of them are quadratic residues, half of them are quadratic non-residues. So when you take your composite, this is composite number and it is a product of two distinct odd primes. In that case, phi n by 4 many elements, it is not exactly half of them are quadratic residues modulo n and half of them are quadratic non-residues modulo n. In that case, the distribution is like that. So phi n by 4 many elements are quadratic residues modulo n or square modulo n, and remaining phi n 3 phi n by 4. This many elements are quadratic non-residues modulo n. Okay, this notation we haven't yet introduced this notation. We'll come to that later. Yeah, this notation I have not introduced it. This is Legendre symbol. We'll discuss those things. Okay. So, for example, suppose n equal to 21. So, how many quadratic residues modulo 21? 21 is essentially 3 into 7. So, in quadratic residues modulo 3 are quadratic residues modulo 7 you find. Without knowing the generator also you can find. The way of finding quadratic residues modulus is 13. Okay, so we know 13 is prime. So half of the elements in Z13 star are Z13 star essentially means 0, 1 to this Z13 star means 1, 2, 3 up to 12. So you keep on squaring them: 1 square, 2 square, 3 square, 4 square, 5 square, 6 square. So keep on squaring all the elements in Z13 star. Z13 star is having the elements 0, not 0, 1, 2, 3 up to 11, up to 12. So keep on squaring and take modulo 13. So 1 square modulo 13, it gives you 1. 2 square modulo 13 gives you 4. 3 square modulo 13, 9. 4 square modulo 13 means 16 minus 13. That means 3. 5 square modulo 13 is 12. 6 square modulo 13 is 10. Then when you take 7 square modulo 13, it gives you this one. 8 square modulo 13 gives you this one. Because 7 square, you can write it as 13 minus 7 whole square. 13 minus 6 whole square. And when you take modulo 13, that it becomes minus 7 square, minus 6 square. That means 6 square. So 7 square gives you this value. 8 square gives you this value. 9 square gives you this value. 10 square gives you this value. 11 square gives you this value, same value. And 12 square gives you the first one. So half of them you can see that half of them, if you keep on squaring and reduce modulo 13, the first half of them will give you all the quadratic residues. So this side 1, 4, 9, 3, 12, 10. 12, 10. That's all this, and remaining are quadratic non-residue. So if you don't know the generator, then also you can find in this way the quadratic residues. You can list down all the quadratic residues modulo prime in this way. Okay, so here we have observed if n equal to pq, then how to find the quadratic residues? It is a is quadratic residue or square modulo n. Means we have to check it is square modulo p as well as square modulo q. It is if and only if condition. So n equal to 21 means 7 into 3. So find all the quadratic residues modulo 3 and all the quadratic residues modulo 7. So these are the sets. So 521, so you have to check in 521 star in Z21 star. Z21 star is essentially these values: the number of elements less than 21, positive integers less than 21, and co-prime to 21. You can list all these elements and you check whether this is quadratic residue modulo 3. Also this element whether it belongs to here or also it belongs to here. So 1 is quadratic residue modulo 21. Then 2 it belongs here but it does not belongs to here. So 2 is quadratic residue modulo 7 but it is not quadratic residue modulo 3. So 2 is not quadratic residue modulo 21. So this way you can find out which are quadratic residues modulo both 3 and 7, and that you put here, remaining here. Okay, so you do this exercise by your own. Okay, so in Z21 star you can list the whole set, how many elements it will have, 12 elements, and then you can split this into two sets. One set having 521 divided by 4 many elements, that means 12 by 4, 3 elements, and the remaining elements are quadratic non-residues. Okay, so this one will be my last definition, okay, for today. So what is this? A belongs to Qn. A is quadratic, A is square modulo n. Okay, A belongs to Qn means A is square modulo n. That means there exists some x belongs to Zn star such that x square is A modulo n. A is square. Okay, A is square of x modulo n. Then this x is called square root. A is square modulo n, and this x whose square is A modulo n, this x is called square root modulo n. Okay, this also we need, this concept also we need. Square root, finding how to find the square roots modulo n, how many square roots we will have. Okay, so if p is prime, if this n is prime, then how many square roots we will have? 2 square roots. One is x, one is p minus x. Okay, so here I have written, if p is a not prime and a is a square root modulo prime p, then a has exactly 2 square roots modulo p. So there exist exactly two values of x that satisfy this congruence equation, x square congruent to a modulo p. And those values are essentially x and p minus x. These are the two square. Because you can see if you get a solution of this x, then x is satisfying, and p minus x, if you put p minus x here and you just write it as p square minus 2p plus x square and take modulo p, then x square minus 2p terms means p square minus 2p terms, p square minus 2px, that term vanishes. So essentially you are getting the same equation, same congruence equation. Okay, so if P is A is quadratic residue modulo A and odd prime, then the square roots of A modulo P are given by x and P minus x. Okay. And more generally, if n has the prime factorization, this p1 to the power e1, p2 to the power e2, p2 to the pk to the power ek. Okay, where these pi's are all distinct odd primes, and these ei's are positive integers. e1, e2, ek are greater or equal to 1. Then, and if A is a quadratic residue modulo this n, A is quadratic residue modulo this n. Then it has precisely 2 to the power k distinct square roots modulo n. We have seen if A is in Qn, n is of this form. We have observed just here, if n is product of two primes, then A is square modulo n or quadratic residue modulo n, if and only if it is quadratic residue modulo p, and it is also a quadratic residue modulo q. Same concept holds here also. If A is square or square modulo n or quadratic residue modulo n, where n is this, then A must be quadratic residue modulo P1, A must be quadratic residue modulo P2, as well as A must be quadratic residue modulo Pk. That means if A is a square modulo n, then A must be square modulo P1, it must be square modulo P2, it must be square modulo Pk at the same time. Okay, this condition holds. Now, what is the condition that A is quadratic residue modulo P1? So we are saying we have to solve this system of equations. So we have to solve we have to find x such that x square is congruent modulo x square. This equation x square is congruent to a modulo n. N is this. So this equation is converted to system of this equation. X square is congruent to a modulo p1, x square is congruent to a modulo p2, x square is congruent to a modulo pk. Okay, where p1, p2, pk are pairwise mutually distinct. So you have to apply Chinese remainder theorem. So you have this single congruence modulo n converted to this system of linear this is not linear equation, system of equations, system of one congruence is converted to system of equations. Okay, so now it is prime. Now first equation is prime. So it has two solutions. If it is prime, then I know it has two solutions, x and p minus x. So from here I get two solutions. From here I get two solutions, and from here I get from each equation I get two solutions in this system of k equations. Now from this first equation, among two solutions you take one. So it has two solutions, two possibilities. From there I can take one. It has also two solutions. Here modulo p1 I have two solutions, modulo p2 I have two solutions, modulo pk I have two solutions. So every solution, from one solution you pick from each, you get one solution. You take another solution from here and remaining here. So generally means precisely we have 2 to the power k many square roots modulo n. Modulo p1 we have two solutions, modulo p2 we have two solutions, modulo pk we have two solutions. Okay, so we get x modulo p1 Also P minus X modulo P1, X modulo P2, P2 minus X modulo P2. Okay, so this way you can when you combine them, you can get precisely 2 to the power k many distinct square roots modulo n. Okay, so the square root modulo of 12 modulo 37, square root of 12 modulo 37. So these are 7 and 30. So this is 37 is prime. So it has two solutions. 7, we say here x equal to 7 and x equal to 37 minus 7. That is 30. 7 and 30, these are the two solutions. Now if you are asked to find the square roots of this is 121 modulo 315. Now 315, this modulus is essentially multiplication, means factored in this way. 3 square into 7 into 5. So how many solutions you will get? We have 3 distinct primes. So 2 to the power 3. 8 distinct solutions, and these are the solutions. Okay. Okay. So these are the basic number theory. Some proofs I will cover in subsequent classes. One thing I mentioned that while finding the primitive root modulo a prime, if you know the primitive root modulo prime, then from that you can find the primitive root modulo other composite, other numbers, other modulus. Okay, but the problem of finding the primitive root modulo a prime, it is not that easy. We go for starting from shortest possible primitive element. We keep on checking whether it is primitive element or not. If it is not, then we go to the next possible lowest primitive element candidate, like that. There is one heuristic algorithm. It is called Gauss algorithm for finding primitive root modulo a prime. If your this prime is very large, then you can utilize this. I will not discuss this. I will not discuss this. This is some randomization is incorporated to get the primitive root modulo a prime. Okay, this is not very good algorithm, but some randomness is introduced, randomly selected. Instead of starting from the lowest possible primitive root, it randomly selects one, and then one element and check whether it is primitive root or not. And the next one means it actually reduces the search space. That is the optimization made here. Okay, so let us stop here. Okay.